would like to do what water does. You know, you can float in water, you go deep in water, and it doesn't push on you any harder anyplace else. Dry flotation is really a synthesis of flotation. So when you get into understanding of how a fluid acts on a person floating in and suspended in a fluid, you have to understand that there's low surface tension, 6 degrees of freedom, low friction, and a constant restoring force independent of depth of immersion.
There's surface tension there, but it's very low. So you got to be able to get immersed or penetrate the surface. When you have a person sitting on the cushion, you're always working to get them as deeply immersed as possible. You really want them to enjoy as much surface contact as they could possibly get.
A water molecule can go any place it wants to go. And that's why water can wet any shape that's presented to it. 6 degrees of freedom is basically recognizing you got an axis system in space, and there's 3 axes. There's an X, it's an X, a Y, and a Z. So when you're in space, you work with those kind of axes. Or if somebody's floating in water, they can rotate around any of these axes. So one of the degrees of freedom is being able to go up and down these axes, back and forth. So you're free to do that. You go up and down, that's 3 degrees. The next degrees of freedom is to rotate around the axis. So when you do that, you added another 3 degrees, so the total is 6 degrees of freedom. So if you look at an air cell sitting here, which is a thin, flexible rubber construction, then the air cell is free to go up and down. It's free to twist. It's free to go back and forth. So it has 6 degrees of freedom.
And we do that with all the individual air cells made out of soft rubber, neoprene rubber, that allows the cells to shape and form to the body that it's contacting. The other side of that is friction. You really don't want a lot of friction. So we treat our air cells to be slippery. Friction is the only method of inducing shear loads on the body, and shear loads then induce deformation. Low friction reduces the shear loads and therefore reduces the deformation that induces ischemia. Tissue deficient wounds depend on a granulation process where the exposed capillaries basically create little nodules at the end of the capillaries, and they are slowly but surely recreating tissue. And if you can support that without knocking off the nodules, because that's what happens with these air cells. They basically roll with the tissues, and they don't drag across the tissues. That's a whole other proprietary process that we use to create the low friction cell surface. In essence, we're creating flotation, not using water. Buoyancy within a fluid is very, very steady, very constant. No matter how immersed you get, the buoyancy forces are about the same. So you need a constant force, restoring force to support the person. So no matter how deep you get immersed, it doesn't push back anymore. Normal cushions have a spring rate, so when you push into them, the further you push into them, the harder they push back. So when you have a disabled person and you're dealing with they're emaciated, atrophied, bony prominences are dominant, and you don't want that bony prominence to see more push than the rest of the skeletal system. It's blood flow, blood flow, blood flow. It's the key, and we do that by not changing that person's shape by very much. The shape does adjust with time and forces because we essentially move body fluids someplace else. That's blood, interstitial fluids, and so forth. So the body is very dynamic with respect to blood flow. And for every action, there's a reaction. You just can't get around that. So by maintaining blood flow for long periods of time, we hope and do quite a bit to support tissue viability. And tissue viability, I think, is a key perspective as to how we should think about things. So many of the academic people are focusing on tissue destruction, looking at tissues being destroyed close to the bone and things like that, which is certainly happens, but you really don't want to be there. You know, you want to be operating in a safe zone, and so I guess these are intriguing problems, but it's not where we want to be. We really want to be with tissue viability. You're compressing all those tissues, ducts, whether you're talking about a lymph duct or you're talking about the vascular ducts. So you're putting equal forces, compressive forces on all those. And if you really don't deform them very much, they can still have flow. So fluid flow is the key with maintaining blood flow, lymph flow. And then as you compress the tissues, they become closer and closer to the actual skeletal system that's there, in this case the pelvis. So that shape becomes more and more dominant as time progresses, and we're talking hours now, so that the shape that it gets exposed is more and more close to the bony protrusions, especially like the ischial tuberosity. And that gets to be the most difficult place to distribute forces. People want to talk about pressure redistribution. I don't understand that. I don't believe that's what we're talking about. It's all about force equalization. And if you utilize and equalize the forces, as a Rojo cushion does, then all these areas see the same stress, essentially. You don't get any peak forces deformation.